Hello and welcome to Lecture 2 of Energy Use and Efficiency. And we're going to look at some specific cases of energy use and their efficiencies. And one of those will be how energy gets used by the human body. In your body, or the body of any other animal, you are storing chemical energy from food. And the body stores it in various forms, and I don't mean forms of energy. It's all chemical energy. I mean various different chemicals. And the primary one for short-term use is a chemical called ATP, adenosine triphosphate. But the body lays down longer-term stores in fats. And if you look at some food that I just took out of my fridge, you can see that the energy in this food is indicated. But it's not in the units we're used to. We're used to joules. This is being given in calories, so we'd better talk about calories. So a calorie with a little c is defined as the amount of energy required to raise the temperature of 1 gram of water by a degree Celsius. And it turns out to be 4.19 joules. But the calories in food are capital C calories, or what we often call dietary calories. And a dietary calorie is a kilocalorie. So in other words, one dietary calorie is 4.19 kilojoules. So let's just calculate some energy capacities of foods in joules. The yogurt out of my fridge at home said it had 100 calories, and so we'll just do a typical unit conversion, right? We're converting out of calories and into joules, and 1 calorie is 4.19 times 10 to the 3 joules, and so that's an easy calculation. That is 4.19 times 10 to the 5 joules. And at a well-known restaurant, 1 serving of fries is apparently 323 calories. I don't know how they can give it that precisely when the number of fries you get is rather variable. So let's, think about sig figs, that's not really possible, but whatever. And so, same unit conversion. And so that is, my calculator says, 323 times 4.19 E3 is 1.3, we'll call it 1.4, 1.4 times 10 to the 6 joules. Okay, and look, we're talking hundreds of kilojoules or even megajoules in fairly typical foods. These energies are big compared to what we're used to seeing. So now we come to talking about the efficiency that your body works with. When you take in food energy, that doesn't all get converted directly to work. First, your body will typically store it as fat or as carbohydrates, and it'll convert some of that to ATP as needed for quick use. So at any time, your body is often in the process of converting some carbohydrates to ATP. And then when you're actually doing something, you're consuming that ATP during an activity, it results in a lot of thermal energy. That's why you sweat. There's inefficiency in these chemical processes, and so there's a lot of thermal energy as well as the work that you actually want. And pretty typically, the efficiency of the body is around 25%, depending on the activity. It can vary between 20 or 30% or so. I'm sure it can be lower. It's probably never very much higher than that. So the efficiency, which is the actual work done, divided by the chemical energy consumed, is typically around 25%. So let's use this to estimate something. Let's figure out how high a typical person, say 60 kilograms, can climb using stored carbohydrates. So I said that the body stores some of its energy as ATP and some as fat, but Most of the short-term storage is done as carbohydrates. The ATP is for immediate use. The carbohydrates are the short-term storage and the fat is the long-term storage. And a typical healthy adult stores around 400 grams of carbohydrates. So let's see how high you could climb if you were to convert all of those carbohydrates. Now, I'll just say you would be really ridiculously tired if you actually did this. If you burned all the carbohydrates that your body had stored, then your body would now go into a complicated process of consuming its fat stores and converting that into carbohydrates. And that's a slow process. You would probably fall over and barely be able to move for a little while, and you would have to eat a heck of a lot before you would feel good again. Anyway, let's just see how high you could go. So what you're doing here is you are converting this chemical energy that you have stored into gravitational potential energy. And so the chemical energy consumed would equal the gravitational potential energy gained if this was 100% efficient. But of course it isn't. If it's a typical physiological process, it's probably around 25% efficient. So first of all, let's just work out how much energy we have to work with. We've got 400 grams of carbohydrates, and each gram gives us 4 calories. So that's 1,600 calories. And if you work that out, that is 1,600 calories times 4.19 times 10 to the 3. So 6.7 million joules. 6.7 times 10 to the 6 joules. That's how much energy you likely have stored as carbohydrates in your body. And now our energy conversion process is 25% efficient. So in other words, our efficiency, which is about 0.25, is equal to what we get, right? What we get is that gravitational potential energy over what we spend. That's the chemical energy that we use. And so our gain in gravitational potential energy is going to be 0.25 of our chemical energy burned. And so we're almost done. We can say our mgh is 0.25 of that UChem. And so our H is just going to be 0.25 of our UChem over mg. And I'll just do that quickly. That is 0.25 times 6.7 million divided by your mass of 60 kilograms divided by g, which we're calling 10. Basically 2.8 kilometers. Okay, and if you think of that, that's fairly reasonable. If you were to hike and go through a 2.8 kilometer rise in the day, right? So hiking up a good-sized mountain, you would be really, really, really ridiculously tired. So we're going to finish up the lecture, and indeed finish up the course, with a quick look at something called heat engines. And this is the tip of a very large iceberg, because what we're getting into here is just a little bit of thermodynamics. And I really think everybody should know some thermodynamics, and we only have time for a tiny bit of it. The idea of a heat engine is that you take something and you burn it. And so you're converting chemical energy, perhaps, although it could be nuclear energy, into thermal energy. And this is the important part here, that you're starting off with some thermal energy that you've got from somewhere. And you use that thermal energy usually to create a high pressure gas, right? You boil water or something like that and end up with a high pressure gas, and it expands and you get it to push against something. Now think of what's just happened. You've used thermal energy to boil something or otherwise create a high pressure gas and it pushes against something, which means you can get it to do work on that something and get that something moving. You've just managed to do what we've said is very hard earlier in the course. You've converted thermal energy into kinetic energy. The oldest, simplest example of this is something called Hero's engine, which looks something like this. You have a cylinder full of water, you heat it, and the steam escapes from two outlets, which are angled so they act like little rocket engines, and the thing spins around. But this is how a car engine works. You're burning the fuel to produce the high pressure gases, and they push on the pistons in the engine. And it's how a power plant works. The superheated steam from burning your coal or oil or natural gas is expanding and pushing on turbines, which spin. In any case, what we're doing is we're taking something hot, so that's our high pressure gas at high temperature, and it has a bunch of thermal energy, so let's call that the energy of our hot stuff. This is a hot reservoir is the technical term. And some of that energy gets turned into work, useful work to produce mechanical energy, but you can't convert all of it. Some of it is still thermal energy, and that is expelled to some cold thing, the cold reservoir, usually the environment, right? That's what the cooling stacks of a typical power plant are. And very importantly, one of the laws of thermodynamics tells you you can never convert all of this thermal energy from your reservoir all directly into work. You always have some left over as thermal energy that you have to get rid of. So pretty close to us is the Lingan Generating Station, which is a coal-fired plant rated at 620 megawatts. And I don't know its efficiency, but a pretty typical efficiency for a coal-fired plant is about 0.33. Let's call this rated output P out. And we know if we wanted to say come up with some figures that would be useful in figuring out its coal consumption, which we're not going to do, but you might do it on the assignment, is we would be able to say that that efficiency is the useful work, that's the power output, over the power of changing chemical energy into other forms, right? The rate at which chemical energy is being consumed. And so our rate at which chemical energy is consumed is just the power out over that efficiency. And if you just take that 620 megawatts and divide it by 0.33, you come up with about 1880 megawatts, right? So that's 1,800, so that's 1.88 times 10 to the 39 watts. And so you could now figure out the amount of chemical energy consumed in a day. That's just going to be that power. The power is the change in energy over delta T, so multiply both sides by delta T and you get this. And so that is our power delta U chem of a day, right? So that's 3,600 seconds per hour, 24 hours per day. And if you multiply that all out, you get about 1.6 times 10 to the 11 joules, which if you now look up how much energy is in a kilogram of coal, say, you can work out how much coal the Lingan power plant has to burn if it runs at peak output.